My dear students, in the last class I have explained about the dihedral group, and in the end we have to discuss the dihedral group D2 of a rectangle, and then this class we have to discuss two more dihedral groups of D3 and D4. So now let us start with the dihedral group D3. So the group D3 is a symmetric group of equilateral triangle with the vertices of the units on the unit circle at angles 0, 120 and 240. That is it is the set of all rotations, reflections and combination of these that leaves a shape and position of a triangle fixed. Now in the next slide we have to show the figure and show that the effect of the 6 elements of a D3, because you know that we already show that the order of a Dn is equal to 2n. So order of a D3 is clearly so order of a you know that is equal to 2n. So order of T3 is equal to 2 into 3 is equal to 6. So there are 6 elements. There is a 6 element, 3 reflections, 3 of the rotations, and then we have a reflection and the combination of a rotation and reflection. So let note that K, S and T can equally be considered as a rotation. Theta is equal to 180 degree in R3, about the axis is K, S and T, and these 6 operations and form a group. So now this I just said that is equal to, we have to write into this form. This the first one is, I just take this equilateral triangle, and this triangle is if we have a no R0, we have to rotate it about the 0 angle, so this is remain the same. There is no changes into this. Now we have to this again we have to just say that we write this triangles, we have to rotate it this as a 120 degree, the same triangle. If we have to rotate it the 120 degree, then we have to just say that clearly you have to rotate into the 120 degree. So that means you have a moving like this 3 to 1, and the shape remain the same again. And now again we have this same equilateral triangle. Now try to, we have to again rotate this for a 240, or we have to rotate this as a 120 degree again, this second triangle. So we getting the this again, if we have to write into rotating this is equal to R120, again we have to getting the this triangle. So either this we have to rotating the 240 degree, then we have clearly you have a you have a like into the this form is this. So this remain the same. So this is a we have to just say that E, R and R square is the, because we have to taking the R square of this. Clearly I just said this is also going to this. So if we take a composition of a R, with R we have to getting the this. So this we have to do identity, and this is we have to denote it as a R, and this is triangle with rotation is denoted as a R to the power 2. So this complete the all the 3 rotations, and now we have to reflection about this about the this axis. So if about this we can say that, so you just say that so we have to this is I think 2 is missing, is equal to 3, and so this is equal to 1 okay, is equal to 1, and this is equal to, you have again 3. So this is complete the, we have to just say that again the rotations and the reflections of this by reflecting this we have to denote as F. So we have to reflecting by this with the K, and then I denoted as a this is a K, and this is S, and this is rotated along the T. So this is about the K, and then we have to just is rotated like reflected about this. We have to take a this reflection of a this. So we have to just say that, so this is remain, then 3 and 4, 3 and 2 are the changing. So we have a f is equal to this form, and now if you take about this, so this you have a 2 and 3 and 1, and then we have to this is the same as a, if you have a take a composition of this r square with this f, you getting again the same figure. If you have combined these two, rs is equal to this, and then if you take a r and composition f, and this is again the rotation of reflection of this, and this reflection this along to the K, along to the S, along to the T, and if we have to these three, so this is after 3 reflections are into the this form. So we have clearly these are the 3 1 2 3 are the rotations, and these 3 are 1 2 3 are the reflections. So we have to total 6 elements of this group of a DN. Now I just we just write into this form, because R0 we have a like this 1 2 3. So R0 we simply say that 1 2 3, then this is going 1 2 3, and R 120 R 120 we have a 1 2 3, and now see 1 is rotated about the 3, and then we have a so this is changing into this form. So clearly we have to just R1 to R1 is moving to the 2, 2 is moving to the 3, and 3 is moving to the 1 form. And similarly R40, R1, R240, R240 again this is rotated into the 1 at 20 degree. So this is a rotation of 120 degree is equal to 3 1 2 in this form, and we have a reflection RK, we denoted as FAF 1 2 3, fixing 1, and then reflecting this and 2 3 2, and then we have to RS, this is we have to denoting the F, and now RS is equal to, we have a 1 2 3 fixing 2, then 3 and 1 is reflect each other, and then we have a RT is equal to 1 2 3 fixing 3, then 2 and 1, and now we also say that this is R square F. So R square we have to just check, we have R square is equal to this, and F composition is equal to, we have this. So if we take 1 2 3, so he say that R square R this R square and F composition is giving out this note. So we have a F 1 goes to 1, and 1 goes to, you have a 3, and you have a 2 goes to 3, 2 goes to 3, 3 goes to 2, 3 goes to 2, 2 goes to 1, and now you see this is a 3 2 1, that this is clearly this, and this is the same as a R square F. And if we take a composition of this these two, then we have to say that 1 goes to 1, then you get 1 goes to 2, similarly 2 goes to 3, and then 3 goes to 1, and then where 3 goes to 2, 2 goes to 3, and this. So we just say that we can write into this form. So this can be D3 can be written in the form of E is equal to R0, R is equal to rotation about 120 degree, R square is rotation about 240 degree, F is equal to, we have a reflection, then RF and R square F. According to the definition, we just say that we can write into the form of this. Simply F square is equal to identity, and we have to write all the elements of a, because we have a E, R, R square, and then we have a F, and then we have a combination of this RF and R square F. We have to write into the this set is equal to D of 3 by the according to the our definition of a Dihedral group. We have to how to write a Dihedral, because generally we write the Dihedral group of in the form of this R to the power n minus 1, and F RF R square F R to the power 3, and so on. So here we have a like into a this form. So clearly we have to mention into this form by the Cayley table. If you see, this is the identity element. So this is a identity element, we have to identity element, and now we have a identity element, and then we have a identity element, and then we have a identity element. Is so, if by this table, and then you can say that the property of a dihedral group D3 are the same that is the symmetric group of S3, because S3 is also the same types of element. So, properties of a dihedral group D3 and are the same as the symmetric group S3, as they can be treated as a same group. So, we can simply saying that, so we just say that now we move to the, this is clearly this by this table we can easily prove that the is a group, the inverse of a R no identity itself, inverse of a, this is we have to write in the form of a this R0 is equal to identity, R120 is equal to R, R240 is equal to R square, then F, then we have a RS is equal to R square F, and this is equal to we have a RF like this. RK, I just sorry, I just RT, this is RF, and this is a F. RK I write F, this is F. So, yeah, I just shifted this column into this form, is not a problem. So, we have a like this. So, if we take inverse of identity itself, we know that the this is again we have a E R R square, we have a RF R square F, and then F. Now, we know that F square is the identity itself. So, R square, this is giving the R square. So, if I change this table little bit, I just shifting this column to the this place, and then we have to shifting into this form. So, this should look like this R 120 R 240, and then we have a this sorry this 120 R 0 or R 240. So, we can like this, you can just leave this. Okay. So, we just say that this satisfy clearly F square is equal to identity, and then we have a R composition R square is equal to identity, then R square R is equal to identity because it is equal to 3. You just say that R to the power 3 is equal to identity. So, clearly by the here we have to mention R square composition R is identity, R composition R square is equal to identity, and RF square is also identity, and R square F is also identity. So, the properties of our definitions of the dihedral groups is satisfying all as here. So, clearly this is a dihedral group, and all the properties of this dihedral group D3 is the same as a properties of a symmetric group for S3, and they are treated as a same group. Now, we have to move to the another symmetry, and that symmetry is called the square symmetry. Group D4 is the symmetry group of a square with vertices on a unit circle at angles 0 degree, 90 degree, 180 degree, and 270 degree, and that figure shows that the 8 symmetries of a squares are there. We have a this is a rotations R0, there is a no rotation, a rotation about 90 degree, about 180 degree, and 270 degree, then horizontal reflection, vertical reflection, diagonal 1 reflection, and diagonal 2 reflection. Be the symmetric group of a square. This is the D4 is look like into a this form. So, we just say simply this into a is about the this form. So, this is the I just say that if we take just no changes are there. So R0 we have to identity, then it looks the same figure. This both are the figures are the same. Now if we have to R90, so if we have to is to 90 degree, if we have to take a rotate at about the 90 degree, so we have to this is to this form. So this is clearly 4 and this is 1 and 2, then is we denoted as R. Then again we have to the same, we have to divide 180 degree, or we have to rotate is equal to 90 degree. So this is equal to this is same as a this is same as a form of a we have to rotate is equal to 180 degree. So this is 4 and then we have a 3 and then 2 and 1. And again we have to rotate, this is again is a 90 degrees, so then is equal to 4 is equal to 4, and then we have to write into this. So this is we have to denote it as a E, and if we denote rotate is 90 degree is denoted as a R. If we denote rotate 180 degree is equal to R square, and this is equal to we have a R cube. Then we have to just say that because we have a working on a D4. So D4 is equal to, we have to just say that that means R to the after rotation 4 we have to getting the identity. So we have possible rotations are identity, and we have a R square and R cube. Then we have a reflection F, and then we have to just say that is a what is a horizontally. So if we have a reflect, this is a horizontally. If we have to reflect it horizontally, then this shifting is 4 and 3 1 2, and if we have a by this, so we have to just take, and then we have to again by verticals. So verticals means we have to 4 and 1 shifting here, and then 3 and 2 in this way. And then if we have a by this diagonally in this diagonally element, so this means we have to 1 and 3 are shifting. So diagonal 1, and this is again the diagonal 2. We are at 1 and 3 are fixed, and then 4 and 2 are the changes into this form. So in the we have to write all this in the form of a permutations. If we try to write this rotations and reflections of this square in the form of a permutations, R0 we have to like this form. Now you see this clearly, and what is moving this is one where is the 1 place and 2. Now 1 is moving to 2, and 2 is moving to 3, and 3 is moving to 4 place. So that means R90, 1 moving 2, 2, 3, 3, 4, and 4 is equal to 1. Then again 180 degree, then this is R90 can rotate about 90 degree. So this rotate 90 degree means 1 goes to 3, 2 goes to 4, and then this we have a similarly we have to this. And again we have to rotate this 180 degree means R80 again 90 degree rotating, then is equal to you have a 4 shifting here, 4, 1, 2 and 3. These are the. So clearly we have to write this as horizontally. We have to this figure we have a like this. We have a 1, 2, 3, 4, and then 1 and 4 are shifting, so 1 goes to 4 and 4 goes to 1, and we have a 2 and 3, so 2, 3 and 3, 2. And similarly, if we have to for this is equal to horizontal vertical, so this means this is equal to we have a 3 and 2 sorry 4, and in this way we have to 4 and 3 and 1 and 2, so 1 2 and this 4 and 3, and then we have a by the this diagonal we have a 4 2 1 3, 4 and 2 are a fix. So we have to just say that this is equal to 2 and 4 are fixed, and then 3 and 4 are reflected. And then again other direction, this diagonal we have a 4 3 2 1, then 1 and 3 are the fix, and then 2 and 4 are the changing this position. So this way we can write all the 8 elements of this symmetries reflections. So if we write in the form of a R naught, R 90, R 180, R 270, H V D D prime, and if we take a compositions of this, and now you see if we have to take a R 90 or H is giving to R 90 and H, R 90 is equal to this, and then you have a H is equal to this. So if you take a composition of these two, 1, 2, 3, 4, R 90 composition H, so H is 1 goes to 4, 4 goes to 1, 2 goes to 3, 3 goes to 4, 3 goes to 2, 2 goes to 3, and then 4 goes to 1, and 1 goes to 2. So what is this? This is the form of a 1 4 3 2 and 1 4 3 2, that is equal to, we have a D prime. This is the same as a D prime. So you just see this is R 90 or H is equal to D prime, R 80 H is equal to V, and then similarly all the compositions we can write into the this form of this table. We just say that I just denoted in the form of this R R is equal to 90, R is square, and R cube is equal to this. F is equal to, we have to denote it as a H. Then we have a RF is equal to, we have a D prime. Then you just see this R 90 in this, and R square R 180 is equal to V, and R cube is equal to this is equal to similarly. So I just say that into this form, and now note that this group is a non-abelian, since H and 90 is equal to D, and R 90 is equal to D prime. Now just see in the form this is equal to, you have a H is equal to, you have a D, and then we have a H into R 90, then we have a getting is equal to D, but in this case is equal to D prime. So by this figure we can say simply this Cayley table, we can easily say that this is a clearly is a non-abelian. The D4 can be simply written in the form of a E R square R cube, and F R square F R cube F, according to our definition of a dihedral group. And then we have a since clearly this is a example of R 90, this is as a non-abelian group because it is not commutative. If you want, we can verify this R square. We have to R square F is equal to V also. So for example, this is E, not a problem, R square R to the power 3, and this is equal to F, and these three are the combination of these. So we have to calculate the R square F. Of R square F is equal to 1 2 3 4. So we have a 1 goes to 4, and 4 goes to, you have a 2, and then we have a 2 goes to 3, and then 3 goes to 1, 3 goes to 2, and 2 goes to 4, 4 goes to 1, and 1 goes to 3. Now you see 2 1 4 3, and that is equal to, you have a V. So this is 2 1 4 3, this is nothing but is equal to is a R square F. Now we have to take a R of F. R of F is equal to 1 2 3 4, 1 goes to 4, 4 goes to 1, 2 goes to 3, 3 goes to 4, 3 goes to 2, 2 goes to 3, 4 goes to 1, 1 goes to 2. Now you have a 1 4 3 2, and that is equal to simply is a D prime, and this is nothing but is equal to RF. And similarly we have to calculate the R cube F. So R cube F is equal to 1 2 3 4, and R cube F is equal to 1 goes to 4, 4 goes to 3, 2 goes to 3, 3 goes to 2, 3 goes to 2, and 2 goes to 1, 4 goes to 1, 1 goes to 4, and now this is nothing but is equal to D. So this is clearly we have a R to the power 3 into N. So ultimately we have to write all the elements of this are the form of a identity R square, R rotation R cube, and the reflection, and then combination of all this rotation and reflections. So this is clearly, now we have a remark. Order of a Dn we already explained u is equal to Tn, and order of a D4 is equal to 8, and then Dn n greater than equal to 3 is a non-abelian group, because we have to show that D2 is equal to 4, and D2 we have a take a rectangle, and this is the abelian group. And then this is the same as you have a E, A, B, C. This is called as a Klein-4 group, and this Klein-4 group is clearly is an abelian group. So all the groups Dn where n is greater than or equal to 3, we have a, because D3 you take it, D3 is equal to is a 6th order group, and this is the same as a S3. So that means this is clearly, we know that S3 is a non-abelian group. So this clearly we have to show that this n for all n greater than equal to 3 is a non-abelian group. D4 is, if this is, then clearly D4 is a non-commutative group. In D4, order of a R90 and order of a 270 is equal to 4, and order of a this and this is equal to 2. Now just check, if we have a D4, you can just say that we take a R90 and R270 is equal to, so this is R90, means we have to take a order of a R and order of a R square, that is equal to 4, and order of R to the power 3, and order of F, order of RF, order of R square F, order of R to the power 3F, they are all 2. We can easily verify by the this. You can just take because for R we have a simple is equal to 1, 2, 3, 4, then we have a 2, 3, 4, 1, and now just say that. So this is 2, 3, 4, 1, and then if you take a, because it's order of a 2 multiplied by is again itself, so this is getting 1, 2, 3, 4, 1 goes to 2 and 2 goes to 3, 2 goes to 3, 3 goes to 4, 3 goes to 4, 4 goes to 1, 4 goes to 1, 1 goes to 2, and then again we have a square, and then we have to multiply it again this, we have to getting 1, 2, 3, 4, 1 goes to 2, 2 goes to 4, 2 goes to 3, 3 goes to 1, 3 goes to 4, 4 goes to 2, 1 and 3. Now again multiplied by this, we have to getting 1, 2, 3, 4, 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 2, 3 goes to 4, 4 goes to 3, 4 goes to 3, 3, 3 goes to 4, and then clearly is equal to identity. So this is, we have to take a R. So we take clearly order of a R is equal to 4. Similarly, order of a R square is equal to 4. Order of R to the power 3 is equal to the 2, and similarly order of F square take similarly you can solve the order of these all elements are the 2. Now D4 is not a cycle since it is not abelian. Also since there exists a no element whose order is 8. So we have to just check clearly D4 is not a cyclic group, because the first condition is not an abelian. If it is cyclic, then there must be an elements of order 8, and D4 has no elements of a order 8 into case. Okay, so now we have to another remark, Dn and N3 is not abelian, so D3 is also Dn is for all n greater than equal to 3 is not a cyclic group. D2 is abelian, but it is not cyclic, because in D2 again there is a no element of a order 4. So because all the elements of a order 2 is there, so this means clearly D2 is also is not abelian. Now we have to each finite set of a D4 we writing the R0, and this we have to just say that identity R square R to the power 3, and then we have a this is clearly other set, and this is also set this all three set. These are is a closed with respect to composition or permutation, therefore these are the proper subgroup of this D4. So clearly this means we can write in the form of a identity R square R f and R square f. So, this is clearly all are the these are the form these are the proper subgroup of a this dihedral group D4. Also, number of elements of order T in Dn is n plus 1 if n is even and n if n is odd. So, number of elements of order 2 you just take if you have a D4 then in D4 order of number of elements of a order 2 if n is even. So, 4 plus 1 is equal to 5 and now you just see this way. What is this going? Okay. So, this means 1, 2, 3, 4, 5 there are the element of a 4 elements which is order is equal to 5. Now, for a similarly if you check for a other. So, this means we can clearly say that this is the formula we can using this number of elements of order 2 in Dn is n plus 1 if n is a even and n when n is a odd. Okay, so now another this remark is saying that if 2 does not equal to d divides n, the number of elements of order d in Dn is 5d. And similarly, we can say that S1 and S2 are cyclic. So, D1 and D2 are the cyclic. We can say that simply is equal to and Sn n greater than or equal to 3 is a non-abelian and again is a not cyclic. So, now I think I have to stop this today's lectures here. We complete the portion of in these two lectures the dihedral groups. I hope you have to understand the importance and very good examples of this dihedral group, and we can extend this symmetry for a in place of a D4 we go to the D5 and D6 also. So, but it is very complicated figures going on this form. So, we have to again rotation into this. Rotation is simply the 360 by n. If we have a 4, then if we have a like this rotations. So, 9 we have to theta can be written as 360 over 9 n. If we have to D3, so 360 over 3. So, we have a 120 rotation. D4 is equal to we have a 360 upon 4. So, we have a 90 and D2 is equal to we have a D2 is equal to 360 upon 2 is equal to 180. So, that is why I just starting the rotations by the 180 degree, 90 degree, 120 degree and then we have a 90 degree for all these three rectangle, equilateral triangles and this square. So, I have to stop today's lecture here and then in the next class we will continue to the alternating groups, and after alternating groups we start the cosets and then continue the Lagrange's theorem. So, thank you very much.